In this video, we're going to take a look at some more applications of calculus to polar coordinates. So we're going to look at area and arc length in polar coordinates. So let's start with area. I'm going to draw a region, and we're going to say that that region is defined or bounded by some polar curve. So let's call that region R. So if a region R is, so if it is a region bounded by R equals f of theta, some polar equation, or an equation for a polar curve that looks like this as a function, between theta equals a and theta equals b. So we have an upper and lower bound on theta, and we have our outer bound in R defined by our curve. So if this is the region where f, let's make sure that our f is positive and continuous, so that we don't have to worry about negative areas or anything like that, with 0 less than b minus a less than or equal to 2 pi, then the area of R is the following. Okay, so I'm about to write down the formula, but let me just go through each of these real quickly before we write it down. So we're going to have a region R. Let me draw it real quickly. So let's say that this is the positive x-axis, this is the positive y-axis, and maybe we're starting at this angle, so this is the angle theta equals a, and maybe we're ending by the time we get over here somewhere. This is where theta is equal to b, and we have some curve in between doing whatever it happens to do. So the only requirement of this curve is that it is positive, meaning the radius is over here in the positive direction. We aren't having a negative value for r that puts it down into this quadrant. So it's out in the positive direction. And it's continuous, right? It doesn't have any gaps. And then this has to be true. Basically, the span from our starting angle to our ending angle, which is b minus a, needs to be less than 2 pi, or equal to 2 pi. So basically, I can define it for like one full rotation, but if I let it go any further than that, if we rotated more, went around more than once, the area no longer makes sense. It no longer makes sense to talk about the area of like a circle if you're saying, I'm going to let theta go like this. It's going to go all the way around twice, right? You only have one region. You're defining it doubly by spinning around twice, and this becomes basically not a function anymore. So this condition here is just saying, really, you can only go up to one full rotation between your starting point and your ending point. That's really what that requirement is saying for this to make any intuitive sense. Okay. So with all of that, the formula that we're going to get for our area is the following. We're going to integrate from A to B, and the formula looks like this. It is 1/2 times f of theta squared d theta. Okay, so where on earth is this coming from? What we're going to have to do is look at this picture and get a sense of exactly what's going on here. So where does this come from? Another equivalent way to think about this is, so let me just write another equivalent form, is also the integral from a to b of 1/2 r squared, right? Because we're really thinking of this f of theta as being equivalent to r. That's how we're defining it here. So that might make a little bit more sense. It's the way that we're defining our r. Where r equals f of theta. So these are really saying the same thing. It's depending on whether I'm explicitly plugging in f of theta or just calling it more generically just r, but r is represented by f of theta. Okay, so why? Why does this formula work? Let's think about how we're going to slice things up in polar coordinates. We can't do it in rectangles anymore, because when we're dealing with our polar coordinates, we have one that represents length and one that represents angle. So instead of chopping up things into like a little bitty tiny pieces of either dx or dy, I'm going to do it in tiny little pieces of d theta here. I'm chopping it up into a bunch of little tiny d thetas, but that means a little tiny angle. So that means here would be the first little angle. And then here would be the next little angle. And then here, and so on. And what we're going to do is basically chop these up in such a way that we get a bunch of little tiny triangles out of these things. And then we're going to sum up, right, all these little areas of these little triangles. So d theta is what's small. And so we're looking at these little sections here. If we zoom in, what essentially we're doing is I'm going to represent these as little sections of circles, basically. I want to treat each one of these slices as a little section of a circle. So these are the shapes that I'm trying to use, basically. So some tiny little section of the circle. The angle that we're using here is some little tiny d theta. And what we're going to pick is just one r value. If we shrink d theta small enough, eventually this side and this side will sort of converge and we'll have one specific value. So what is the area of this little section? This is the area of section of a circle. So it's a little tiny d theta. That's the angle that we're using. And how do we get the total area? Well, if I know what this radius is, so let's say that this is the radius that we're using, I know that the area of the whole circle is pi r squared. So the area of our little section is going to be some fraction of pi r squared. But what is the fraction that we're going to get? Well, if we're only doing a little tiny d theta for our angle, what fraction is that of the whole circle? Well, what's the total, angle to span an entire circle, go around an entire circle? It's 2 pi. So our fraction is just a tiny little bit of d theta out of a total of 2 pi. D theta is our tiny angle, 2 pi is the full angle of the circle, and this will get the fraction that we need that we're looking for. So this is the fraction of the entire circle that we're using. So our area is going to be d theta over 2 pi times pi r squared. And what happens? The pi's cancel, and we wind up with 1/2 r squared d theta. That is the little area of this little piece. Then what do we do to all these areas of all these little pieces? We add them up, and that's where the integral comes from. So this piece right here is why we're plugging in this piece right here. It's a little tiny sliver of area. So that's where this formula comes from. We're adding up a bunch of these little tiny slivers of the full circle. So as an example, let's find the area of a particular region. So let's say I want to find the area of r equals cosine of theta between theta equals 0 and theta equals pi over 6. So for us, our area, which in general is going to be, again, from some a to some b of 1/2 r squared d theta. That is our formula right here. 1/2 r squared d theta is going to be equal to the integral from 0 to pi over 6 of 1/2. Our r is cosine of theta squared d theta. That's the area. So that's just plugging into the formula. How do I integrate this thing? So I can pull out a 1/2 in front. We've got our integral from 0 to pi over 6. And I'm now trying to integrate cosine squared of theta d theta. To do that, we need to use our power reduction formula. So I need to take it from cosine squared to the following. So same integral, but cosine squared of theta is equal to 1/2 plus cosine of 2 theta over 2 d theta. And that is something that I can actually now integrate. So I've got my 1/2 out in front. The integral of the 1/2 is going to be 1/2 theta, or just theta over 2. And then this other portion, the cosine of 2 theta, will integrate to something involving sine of 2 theta. I have the factor of 1/2 in there, but I also need an additional factor of half, because when I take the derivative of this, the sine of 2 theta, I will get cosine of 2 theta, but by chain rule, I will also get a factor of 2 that I don't want. So this is actually sine of 2 theta over 4. One of the halves is to cancel the 2 I'll get from the chain rule. The other half is to account for the fact that I started off with a half. So there's the result, and I'm just evaluating between 0 and pi over 6. These are important. You can't always just assume the lower bound when you're plugging into trig functions. If the lower bound's 0, you can't just assume it's going to give you nothing. In this case, it will, but if this had been a cosine instead, when you plug in 0 down here, cosine of 0 is 1, and you don't wind up with 0 contributions. So just be careful when you plug in 0 and you're dealing with trig functions. You don't always get 0 in those scenarios. But in this case, that's what we're going to get. I'll plug it in. We will get 1/2 times, when I plug in the pi over 6, I'll get pi over 12 plus plugging pi over 6 here. So pi over 6, when I plug it in here, I'll get 2 times pi over 6. So I double pi over 6 to get 2 pi over 6, which is pi over 3. The sine of pi over 3, the y-coordinate, that's root 3 over 2. So I'm going to get root 3 over 2, and then dividing that by 4 means I will also wind up with another, well, whatever, we'll just write it over 4. And that's the upper bound plugged in, and from that I'm going to subtract off the lower bound, which in this case is 0 plus 0. 0 over 2 is 0, sine of 0 is 0. So those do, in this case, contribute nothing, but that doesn't always happen. If that had been a cosine, we'd have some stuff there. And so what do we wind up with? I think that's going to be pi over 24. And this other number, I'm getting what? Root 3 over, really have an 8 down here, so over 16 when it's all said and done, if we want to write it like that. And so that would be totally fine. You could combine it into a single fraction if you'd like, but it doesn't really matter. So I'll just leave it like that. So that is our area. Just as an FYI, if we want the area between two polar curves, what we need to do is the following. So let's say that one is r of f of theta and the other one is r equals g of theta, where, let's say for the interval that we care about, let's say that the f of theta is uniformly larger than the g of theta. So it's the outer curve. F of theta is outer, so to speak, because the radius is larger there. Is the following. So essentially what I'm saying here is the same thing. Here's some starting angle, here's some ending angle, here's some inner curve, here's some outer curve. This is our f of theta, this is our g of theta, and this is the region R that we're interested in. Y, X, here's our theta equals A, and our theta equals B. So this region in here, right? So it's the region between G and F. And again, where G on the interval that we care about is uniformly less than F. Maybe G is bigger than F other places, but in the interval that we care about, G is less than F. So in that case, the area would be equal to, I'll just pull that 1/2 out front, integral from A to B, and it's going to be f of theta squared minus g of theta squared d theta. So it's the same formula as we did right here. I've just pulled the 1/2 out, and we have two different r's, outer r squared minus the inner r squared. So if you want, you could treat that as like capital R squared and lowercase r squared or something like that, if you wanted to think about it that way. Okay, so for example, to put this to use, what if I wanted to find the area inside of r equals 3 cosine theta and outside of r equals 1 plus cosine of theta. I'm going to give you what these curves look like, and feel free on the homework, for example, to plug these into Desmos to get the equations. But basically, it'll be similar on the exam. I'm not going to give you, I'm not just going to assume that you know how to graph things like this. It doesn't necessarily always matter, but I might as well just give you the picture. I don't want this to be a class on how well you are, or how well you can graph polar functions. So this first one we've talked about, r equals a constant times cosine theta, that is a circle, but it's a circle that's like tangent to the origin. That is, again, a terribly drawn circle, and its diameter is 3. And this other shape, when we have 1 plus, it winds up distorting the circle. And in this case, we get something that looks like this. It's called a cardioid, and it's going to basically go through this point right here, back like this. Let me undo that. That's slightly better. And so we want the area. This one is r equals 3 cosine of theta. And this other one down here is the r equals 1 plus cosine of theta. And we want the area that's inside the circle, but outside the heart shape. And so it winds up being this crescent moon shape. That is the region that I want the area of. So that is our region of interest. The first thing I need to do is figure out where these intersections occur. And what I need to figure out is not the actual xy coordinates, but I need to figure out this angle theta of where that occurs. What angle does that occur at? Because that's how, that's the information we need. That's the parameter we need to do our integration. So where do they intersect? We set them equal to each other. So find the intersections first. So I'm going to set 3 cosine of theta equal to 1 plus cosine of theta. Let's zoom in a little bit here and solve. So I'm going to subtract cosine of theta from both sides. I will get 2 cosine of theta equals 1. Divide both sides by 2. I will get cosine of theta equals a half. And that tells me that theta is going to be the arc cosine of a half, the angle whose cosine is a half. Cosine is the x-coordinate. This turns out to be pi over 3. So this one is pi over 3. This one down here would be an angle of negative pi over 3. Because again, these are non-unique, could also go around multiple times. So here is our answer, pi over 3. That is this angle right here. So this angle that I called theta turns out to be pi over 3. And so we have a couple of options. I can integrate from negative pi over 3 to pi over 3 because we're finding an area and I can see that there's some symmetry to this. I could just do 0 to pi over 3 and then double that to get the total area. So make your life easier however you can. And I'm going to do the easier. So I'm going to use symmetry. And integrate from theta equals 0 to pi over 3. Then double the answer. But you could just as easily go from negative pi over 3 to pi over 3. And that would give you the entire area without having to double anything. So my area is going to be I have that factor of a half out in front. The integral, I'm doing from 0 to pi over 3. And because I'm doing only half of the interval, I also need to double everything out here. So I'm going to put a 2 times in front, which is going to immediately, very nicely cancel with the 1/2. So that 2 came from doubling everything by symmetry, because I'm doing 0 for my lower bound, and it immediately cancels with that 1/2. Now I just need the outer radius squared minus the inner radius squared. So the outer radius at any given one of these points is the circle. It's the 3 cosine theta squared term. So the 3 cosine of theta squared. From that, I'm going to subtract, zoom in, try to write a little more neatly here. The other one was 1 plus cosine of theta squared d theta. Let's make it clear we're integrating that whole mess. So what we'll do is actually go ahead and basically FOIL these out, and then we will collect like terms, try to simplify, and then integrate from there. So the 1/2 and the 2 canceled, so I'm just left with the integral from 0 to pi over 3. This first term when I squared is 9 cosine squared of theta. The next term I'll have minus, let me put it all in parentheses and we'll distribute that through theta. So this times itself is 1 plus 2 cosine of theta plus cosine squared of theta d theta. So we'll collect our like terms. I have 9 cosine squareds, and I'm going to subtract a cosine squared, so I'll wind up with 8 cosine squared of theta. I've got a minus 2 cosine of theta, and I have a minus 1 d theta. So distributing that negative sign through and collecting like terms. This first piece, we have to use the same technique we just used. I can't integrate it directly, so I need to apply the power reduction formula. But this guy's ready to integrate, and this guy's ready to integrate. So we just have that one term to do that on. And I will get 8 times 1/2 plus cosine of 2 theta over 2 minus 2 cosine of theta minus 1 d theta. So far so good. Again, if we want, we can try to, combine some like terms, minimize the stuff that we need to integrate here. So when I distribute this 8 through, this will give me 4. I'm subtracting 1. I'll eventually wind up with just like a total of 3. So that 3 is all the constant, the 8 times 1/2 minus the 1. I'll have this 8 times this term will give me 4 cosine of 2 theta. And then I also have minus 2 cosine of theta. And those are all nice now and easy to integrate. So let's do the integration. I will get 3 theta. For the next one, I will get something that involves sine of 2 theta, sine of 2 theta being the integral of cosine of 2 theta. But again, I need to make sure I get the appropriate correction. So when I take the derivative of sine of 2 theta, I would get 2 cosine of 2 theta. But in reality, I need 4. So I need an extra factor of 2 out here to account for exactly what we get. Or essentially, you could think of it as a 1/2 times the 4. Gives me this 2 here. But this, when I differentiate, will give me what I've got there. So I just have this term. The integral of cosine is just sine. So this is going to be times the sine of theta. And I, again, am evaluating these now between 0 and pi over 3. So we'll plug in. And I will get 3 times pi over 3 is just going to be pi. Plus 2 times the sine of 2 pi over 3. Let me just write it as 2 pi over 3 for now. We'll come back to that. And then minus 2 times the sine of pi over 3. So there's the upper bound. And then for the lower bound, plugging in 0 here, I'll get 0. Plugging in 0 here, I will get 0. Plugging in 0 here, I will get 0. So all of those are going to give me 0 at the lower bound. So on our unit circle, again, what is the sine of pi over 3 and the sine of 2 pi over 3? So here's our unit circle, angle pi over 3 is right here. 2 pi over 3 would give me basically a mirror image of that right over here. The sine is the y coordinate. This occurs at the point 1/2 comma root 3 over 2. So this is the sine of theta, the sine of pi over 3. And this has the same y value. So both of these are going to be root 3 over 2, root 3 over 2. And what we wind up with is simply pi plus root 3 minus root 3, or just pi. And there's our answer. The area between these two curves, this crescent moon shape that we've got, is simply pi. Whatever the units are, you know, because it's an area, unit squared. Let's do one other. I said we were doing area and arc length, so let's do arc length. Arc length. I will just give you the formula, and it's relatively straightforward, but the length of a curve is going to be given by the following. L is going to be the integral from a to b, so that's going to be our starting and ending points in terms of theta, and we get the following. It's going to be r squared plus dr d theta squared times d theta. So that's going to be the formula. And essentially, this comes from doing our parametric version, where we had, if you'll remember, it was basically dx dt, or in this case dx d theta squared plus dy d theta squared d theta. So this is the formula. In fact, I don't need to put this in parentheses. Let me just flesh this out fully so we can actually see where this goes. So this is our old equation. So this was our parametric form. All we need to remember now is what these derivatives actually look like. So remember that x is equal to r cosine of theta, y is equal to r sine of theta. And to be totally explicit, I guess I should say it's really r of theta, cosine of theta, and y equals r of theta, sine of theta. The r itself is a function of theta, right? It's our f of theta, so to speak. So when we take these derivatives, dx d theta and dy d theta, and plug them into our old formula, our old parametric form over here, we'll wind up with the answer that we're getting. So what is dx d theta? I need to take the derivative of this with respect to theta. And again, it's a product. So I'm going to get, you could think of it as first times the derivative of the second plus second times the derivative of the first. So first times the derivative of the second plus second times the derivative of the first. So I'll just call that r prime times cosine of theta. Actually, let me write it out instead of writing it r prime. Let me write it as dr d theta, because that's the notation I'm using above. So dr d theta, cosine of theta. So first times the derivative of the second plus second times the derivative of the first. That's what we've got here. Similarly, I'll have first times the derivative of the second, and this should have a negative sign. So over here, first times the derivative of the second, derivative cosine is negative sign. Let me not screw that up and miss that sign. Down here, we don't have the negative sign, so first times the derivative of the second is going to be r times cosine of theta plus the second times the derivative of the first. So dr d theta times the sine of theta. And now I need to just square these things. So, and add them up, because that's what we do. We square them and add them together. So dx d theta squared is going to be the square of this whole mess. So what I will get, essentially we're foiling it out. It'll be this times itself, 2 of this times this, plus this times itself. So I will get that first term times itself will be r squared sine squared theta. The negatives disappear because we squared it. Then I will get 2 copies of this times itself. So I will get plus 2. We have that negative r and the dr d theta and a sine of theta and a cosine of theta. And let me switch that sign out in front to make up for the negative sign. So again, that's this times this. We get 2 of them when we FOIL. And then I'll get this times itself. So I'll also get dr d theta squared cosine squared of theta. So that's what this term looks like. What does the dy d theta term look like? So now I'm foiling this one out with itself. So I'll get this times itself, which will be r squared cosine squared of theta. I'll get 2 of this times this, which will be plus, in this case, 2r dr d theta sine of theta cosine of theta. Right? R times dr d theta and a cosine of theta and a sine of theta. Here they all are, and we get 2 of them. And then lastly, this term times itself. So all I'm doing is foiling these out. Again, if you have any doubts, write it out yourself and do it more carefully. We wind up with a sine squared of theta. So here they are squared. Now we need to add them up. So adding, we get a bunch of things. So I'm going to collect these terms together. I'm going to get an r squared times a sine squared of theta plus a cosine squared. I'm going to add these 2 terms together. And what happens to them? 0. They cancel each other out. And then these 2 terms, I'm going to get dr d theta squared times, again, a sine of squared of theta plus a cosine squared of theta. That's just 1. That's just 1. These 2 terms canceled when we added them. And we wind up with simply r squared plus dr d theta squared. And so when it's all said and done, dx d theta squared plus dy d theta squared simplifies to just r squared plus dr d theta squared, which is what goes in right here. So this is really the formula. We just derived it. You don't need to derive it every time. You just need to plug into the formula, but that's where the formula comes from. So let's do a quick example. We can finally be done with all of this. Let's find the length of r equals 2 cosine of theta on 0 less than or equal to theta less than or equal to pi. Okay, so in this case, I want to find, I've got my r of theta, so r is equal to 2 cosine of theta. I want dr d theta. We're going to need that as well. So what's the derivative of this? That is, the derivative of cosine is negative sine, so I'm going to get negative 2 sine of theta. And I need to get now this expression to integrate. So r squared plus dr d theta squared is going to be equal to, I'll get 4 cosine squared of theta plus that negative 2 times itself is also going to be a positive 4 sine squared of theta. And this is simply 4. I can factor a 4 out and I'll just have sine squared plus cosine squared. So I just get 4. That whole mess inside the square root for this particular problem simplified to 4. So for us, the L is going to be the integral from 0 to pi. That was our starting and stopping angles, according to up here. And it's the square root of r squared plus dr d theta squared d theta. So for us, that's just the integral from 0 to pi of the square root of 4 d theta. Square root of 4 is just 2, so I've simply got 2 times the integral from 0 to pi of d theta. If we integrate that, I will just get 2 theta evaluated between 0 and pi, which is 2 pi. That is our total length. So this has lengths of, whatever the units are. So that's how we can use it. This is a simple one. Again, you may run into ones that have trickier integrands, but the techniques you should use should match the techniques we've been using. Whenever possible, find a way to turn this into a perfect square to get rid of the square root, or alternatively, see if there's a way to factor it in such a way that we can do a u substitution by having a piece outside that matches as the derivative of whatever's inside. So those are going to be our techniques.